Hello, my name is Patrick Lauer. I'm from the University of Wuppertal, and I'd like to talk about the performance of optimization algorithms for deriving material data from bench scale tests. And thanks to Isabella's great presentation, I may leave out my general explanations on pyrolysis and may directly connect to that point where she said she used literature data and show here another way to get these data. Our aim was to find a good performing optimization algorithm for material parameter estimation to simulate pyrolysis. How did we do it? We compared the best known algorithm till now for this for material parameter estimation with two not yet evaluated algorithms utilizing synthetic data and bench scale tests. So this was our approach. We basically knew the output of the bench scale test and compared it to the pyrolysis model output and alternated the input to the pyrolysis model with these optimization algorithms until the output of the pyrolysis model fits the observed experimental output. And that's how we get to know these parameters. Basically, that's it. The blue line is what came out of the experiment, and we fitted the red line to the blue line. That's what we did. So the bench scale tests were thermogravimetric analysis, TGA, and mass loss calorimetry. TGA has a small sample chamber with a small sample, about a few milligrams. It's a closed sample chamber in a defined atmosphere with a defined heating rate, and we captured the mass loss and the mass loss rate. The MLC has a sample size typically about a few hundred grams. It has a defined heat flux, and we captured also the mass loss and the mass loss rate. Here's a short video. On top, we see the cone that radiates on the sample here that has a heat conducting layer of aluminium. Here is the igniter, and now we see how it ignites. In this case, the sample was PMMA. So which setups did we use? We used one TGA model setup with synthetic data and experimental data. We used PU. Then we used an MLC model with as material PMMA and used an isolating and a conducting, like we saw before, aluminium background layer, and we made two experiments, one with a single heat flux of 50 kilowatts per square meter and one with 5 heat fluxes in parallel for different samples from 20 to 75 kilowatts per square meter. This is our optimization process. We start to estimate parameters, then take out the simulation. We used FDS as the pyrolysis model. And apply a fitness function on the results of the simulation, as that we used the root mean square error function, then checked for the convergency to the experiments, and if it didn't converge, the whole loop began from the start to estimate new parameters, and it depends on the used algorithm how we estimated parameters. So let's come to the algorithms. We have here shuffled complex evolution, an artificial bee colony algorithm, and then fitness scaled artificial bee colony algorithm. The SCE was introduced for hydrologic model calibration. It's an evolutionary algorithm. It's the state of the technology for material parameter estimation. It divides the population into complexes, and these complexes are for a local search, and there is a global evolution between the complexes. This is something specific, you don't have to get it now. And what we used is the ABC that was never used for material parameter estimation. It's a swarm intelligence optimization algorithm. It mimics the foraging behavior of a honeybee swarm and combines the local, the global, and the random search. And it outperforms standard benchmark tests for optimization algorithms, and that's why we choose to try this algorithm. From the mathematics, it's quite simple. It has, after the initialization, 3 phases: an employed B phase, an onlooker B phase, and a scout B phase. In the employed B phase, there is found a food source, which means, in our case, input parameters for half of the bees that were there in the neighborhood of other known food sources. In the onlooker B phase, there is found a new food source based on all the food sources of all employed bees, and the assignment is probability based on the quality of employed bees' food sources. And if there's no new food source found after several iterations, a new random food source is generated. So this is what ABC does. FSCABC is a modified version of ABC. It's introduced for path planning of unmanned combat air vehicles. It outperformed ABC in this specific application, and this is why we choose to test FSCABC on that topic. And it changes only 2 parts in the whole algorithm. The first part is the fitness function for assigning this probability distributed assigning in the unlooker B phase, and the random number generator in the scout B phase. These are the 2 changes. The fitness function is only used by ranking all my solutions and weighting them by the power of a variable named k that has to be determined. And the random number generator is replaced with a chaotic random number generator, which is pseudo-random and travels ergodically over 0 to 1. So every number in that area is somewhere used. So these are the algorithms. And let's now come to the results. The synthetic data was a TGA setup. We used 2 reactions as input parameters, used density, conductivity, specific heat, reference temperature, and reference rate specific to FDS. And our target was the normalized mass loss. So this is how these algorithms performed. What we see is FSCABC is the green line that performed pretty well. ABC converged to a similar simulation, but needed more evaluations. I don't know if you can see it, we used 100,000 evaluations in the whole process, and SCE converges way worse than the 2 other algorithms. I'm not sure if something went wrong here because it was some kind of simple optimization process, but as you see, this yellow line is mostly undistinguishable from the red and blue line that are ABC and FSCABC for the normalized mass over the temperature of our simulation, but the SCE doesn't fit at all. So I'm not sure if something went wrong here, but we will see on the next slides what came out of the other simulations. We had a TGA setup. As I said, we used PU as material, modeled 3 reactions, used as input parameters reference temperature and pyrolysis range, which makes 6 input parameters at all, and used normalized mass loss as in the simulation before as target function. As we see here, FSCABC and SCE perform pretty similar, and their end result after about 10,000 iterations, it's mostly indistinguishable. ABC comes to a similar result, but way later. This is the best fit plotted for the normalized mass, and you can't really distinguish between the target function, the FSCABC, and the SCE function, except for the ABC in this small area. Then we had an MLC setup, used a single heat flux of 50 kilowatt per square meters, used 2 different background layers, the insulating and the conducting background layer, had as material PMMA, had as input parameters density, conductivity, specific heat, reference temperature, and pyrolysis range for one reaction while modeling PMMA, and again used as target function normalized mass loss. So as you can see here, again, FSCABC and SCE perform pretty similar again, while ABC comes to a result in the same area, but needs way more time again. Let's see how this is plotted for the best fit function. Again, you can see in the lower part, this is plotted for the isolating and the conducting background layer in the same colors, and it's hardly to distinguish between all these, so it fits very well. Then we had 5 different heat fluxes on the same sample. We had 5 samples and applied 5 heat fluxes. Had the same input parameters, had the same target, and now we may see that the FSCABC performs a little bit worse than SCE, but as seen before, ABC performs way inferior than both of them. I've left out the plot of the best fit because we had these 5 heat fluxes with each 2 background layers that would be a mess on the graph. So this is what we found out. We showed that 3 algorithms and tested it with synthetic and bench scale data. All 3 generate similar accurate solutions, but FSC, ABC, and SCE are distinguishable better than ABC, while SCE is the most efficient, but FSCABC often is not significant inferior. So the future task may be to tune the FSCABC parameters, because if you get into there are a few parameters you could tune to get a better result, and apply it on other models to show how they react on other models. So thanks for listening. Are there any questions?
Hello. I was just wondering if you compare your optimizer to any genetic algorithm-based optimizer, because there are some published works on some genetic algorithms and on pyrolysis calibration.
But as long as I know, the other genetic algorithm than SCE perform the most worse than SCE, so we used SCE as a quasi-standard for comparison.
Okay.
Anyone else? Okay, well, thank you very much.
Thank you.